Hello everyone, welcome to the show and thank you so much for joining us, whether you're finding us on RTL Today Radio or Apple or Spotify podcast, or you're actually watching us here in the studio from RTL City based in Luxembourg. It is always great to have you listening to my show, watching the show, and I am just so lucky to have a variety of guests who jump into Luxembourg through non-air-conditioned trains. They fly, getting up at 4 a.m. in the morning to come here. And everybody around here today is here for a very specific reason, and one that I care about a lot, which is Asteroid Day Festival in Luxembourg. And we are delighted to be hosting 4 brilliant females in the room, 3 scientists and 1 artist/scientist. So we'll talk about all of that in just one moment. But to introduce you to my guests, I have Aura Satz, Stefania Soldini, Sabina Raducan and Kathrin Altwegg. So welcome to all 4 of you. I know that you've all travelled into Luxembourg. It turns out we were on the same plane yesterday. We didn't know about it. But Aura, because you are the artist and you look at Asteroid Day in a different way, I'm going to come to you just after we do a little bit of the science. So stick with us. Science is not hard. It's going to be very, very exciting. Stefania, I'm going to start with you. You're an associate professor in space engineering at the University of Liverpool and also director of the Zero-G Astrolab, which is a new facility that's recreating on Earth microgravity conditions experienced by the spacecraft operating around asteroids and other small bodies. And you also worked in Japan. You worked at JAXA, the Japanese Aerospace Exploration Agency, on their, for anybody who knows anything about asteroids, very famous Hayabusa 2 mission. And so we're going to talk a little bit about Hayabusa as well. Let's go back. What is an asteroid?
Well, an asteroid is a small celestial object, and you can think of it as like a rocky object that preserves some information, retain information of the early solar system. Basically, some of those asteroids did not manage to form a planet at the very beginning of the solar system formations. And we scientists are interested because retain some clues of maybe how life has been brought to Earth.
And what are asteroids made of?
They're made of different things. There are metal asteroids, there are what we call rubber pile asteroids, carbonaceous materials, so let's say where we want to find traces that kind of related to water. I think in asteroid like Bennu we found traces of DNA or RNA. So again, linking asteroid to life on Earth, but also silicates, so very different material, and also some precious material as well.
Now, asteroids move. They move at different speeds. And you were with JAXA in Japan. This is it's extraordinary engineering here. Talk to us about what Hayabusa 2 was.
So Hayabusa 2 actually still is. Hayabusa 2 is doing so much science. In fact, it's going to fly to a new asteroid on the 5th of July, but we'll tell you in a minute. What is fantastic about that mission is the engineering challenges it had to face. You have to imagine that sending a spacecraft to a small object, which we've never seen before. We don't know how it looks like. We don't know how the terrain is.
Okay, pause. First of all,
challenging.
The first challenge is, how do you know where it is?
Well, we observe it from ground. We have telescope, we track them, and we roughly can guess where they are in a precise manner.
Yeah, there's no roughly about it.
We have to definitely then from there, we know how to target them. And this is a tricky part of engineering, which I find it fascinating. The fact that we exploit the mechanics of the solar system to actually get there.
It really is amazing. And then when you have designed a spacecraft that can reach an asteroid, how do you then go in parallel against it to pick up a little bit of material and bring it back to Earth?
Well, that's I think is the most exciting part. First of all, when you see the object for the first time, you think, oh wow, it's nothing how we thought it was. So the engineers had to redesign completely how they wanted to just touch the surface, because it was extremely tricky to do that with this spacecraft. We had also communication delay, so you can't relay on ground. You have to wait 40 minutes to know is it gone through all right? So there is a lot of challenges from an engineering perspective with very precise maneuver and planning to do this in a timely manner, which is exciting.
So to give us an idea, can you tell us when Hayabusa 2 mission, it was exploring asteroid Ryugu, I'm not quite sure of the pronunciation, but I'm calling it Ryugu. How far away is that from us?
Well, asteroids are around, like, let's say, the asteroid belt is like 100 million kilometers away, so it's very far, and that's what the problem with communication is. We have delay from reaching signal from the asteroids, from the spacecraft to ground, and then wait and send the command again. So for Hayabusa 2 was roughly 40 minutes wait. So,
and then how are you doing the communication relay?
Well, spacecraft have their own antennas. We have grounded this space network on ground, and we have opportunity window to communicate. Hayabusa 2 did operation in a very clever manner. We call it hovering. So the spacecraft is always pointing to the Earth, and then the cameras at the bottom of the spacecraft always pointing at the asteroid. So that type of link and communication allow that to basically always track the Earth and send signal back to Earth, except when the sun was in the way.
It's truly fascinating, and it's unbelievably brilliant engineering. And then it also collected some material.
Yeah, Hayabusa 2 collected material twice, so that's even more exciting. First of all, collected the first layer of material, so this was the first touchdown operation, and then did an impact. So they used an explosive charge to create a small crater, actually it turned out to be 20 meters diameter, to collect subsurface material. This allowed to compare material that has not been exposed by the space weather and the space environment. So this has been done twice, and the sample has been returned to Earth.
I think it is truly fascinating engineering work that you're doing. And how big is Ryugu?
Ryugu was roughly 1 kilometer size in diameter. So that's small body. Gravity very tiny.
Yeah, the amazing thing is when you think about how satellites on Earth to do weather forecasting or looking at crops or water scarcity, sometimes we have a grid of 7 kilometres squared. So you're trying to do engineering around something that's 1 kilometre squared, and I think you said 100 million kilometres away. It's really, I'm not quite sure how the maths works, but it's really quite extraordinary. When it comes to the communication relay back to Earth, will it help when there is possible communication from satellites in space?
So, for instance, if we think about when we had the solar conjunction, was a case in which the sun was basically aligned between Earth and the spacecraft, so the asteroid itself. So we can still receive the signal, but it can be misinterpreted. So it's quite risky sending signal in that case. So we engineered a way to let the spacecraft to operate himself for a month in a safely manner. So we didn't do science in that time. Actually, we did signal science, but we wanted to make sure that the safety in that occasion was primarily the objective, to preserve the mission in that phase where we couldn't do much.
Yeah, well, congratulations. Truly amazing. And also it's pointing to the fact that we need global collaboration to make brilliant science. And in this case, this is with JAXA. Now, moving to ESA, moving to Sabina, I know that you're a planetary scientist. You study impact processes in the solar system, especially on asteroids. And you're going to talk to us about the DART Hera missions at Dimorphos.
Yes, that's indeed what I'm doing. So I'm looking at asteroids. I want to see what they're made of, and most importantly, how they react to an external force like an impact. Stefania was talking about the Hayabusa 2 mission and about the crater that it made. So basically that's where we got a lot of information going into DART because, as Stefania mentioned, the crater was more than 16 meters across.
But I think we should say what DART is.
So DART was a NASA mission. The Double Asteroid Redirect Test was a test on an actual asteroid to see if we can deflect it so that in the unlikely case that an asteroid comes towards Earth, for us to be ready. And it was a complete success.
So we can all feel safe.
We can, so far, yes. So the impact was very successful. We collected a lot of data. So the spacecraft collided with asteroid Dimorphos. So this was a tiny moon in the double system. So a tiny moon around a larger asteroid. So the target was so small. So Stefania was mentioning Ryugu, that was less than a kilometer, while Dimorphos is 160 meters across. So it's even smaller.
And how on earth did you go about doing this?
So 160 meters across asteroid, you don't see it. So that's one of the reasons, between others, that we selected a double asteroid system, because you can see the larger asteroid. So the primary of the system that is almost 800 meters across, and you first find that. So DART had basically a little AI on it to track the asteroid. So it was completely autonomous. Humans were not involved to find the target, because everything happens so fast, and also the communication with the spacecraft takes a long time. So this needs to be done autonomously. So it found the main asteroid first. And the thing is, because the DART spacecraft moved very, very fast, so more than 6 kilometers a second, the spacecraft, the asteroid became visible only about an hour before the impact. So that was the main asteroid. And then the actual target became visible only a few minutes before the impact.
It's quite hard for us here on Earth to think about an object moving at 6 kilometers a second. I mean, the figures, whether they be big or small, either the plus or minus zeros on the end, are so incredible to our minds. How do you mentally think about these things?
So indeed, it's very difficult to imagine what 6 kilometers a second actually means. But we do experiments in laboratory on Earth. So we can reproduce up to about 6-7 kilometers a second in laboratory.
How do you do that?
With very, very large guns, light gas guns. These are entire facilities where you have very small projectiles and you shoot into targets. These guns are as large as an entire room.
The energy is extraordinary.
It is indeed. So it's very, very fast indeed.
Now, let's move on to the Hera mission.
So we had DART. It impacted, was a success. However, we still don't know what was the actual outcome. Was it a crater or not? If it was a crater, how does it look like? And this is where the European Space Agency Hera mission comes. Because Hera, which is now on its way, and it arrives this year, so it arrives early November, will go to this double asteroid system and will see exactly what happened. Will it see the targets? We know that the target is still there, right? We know that the asteroid was not completely destroyed. We saw it on radar. However, we don't know what the crater looks like, if there even is a crater. It's possible that the asteroid was just completely reshaped.
And you're also working on this.
Yes, so Sabina and I work together on the mission, which is quite exciting.
And what's lovely also is, once more, we're showing that the combination of communities, scientists, different universities have to work together, and different space agencies also work together. Whatever the geopolitics of the world, and it does affect space agencies, it doesn't mean that wonderful scientists don't continue to collaborate in the best possible ways.
Obviously, we just do our science. So that's what we are here to talk about today. And part of the things that we've done for DART, for instance, as Sabina mentioned, the impact. In my team, we studied the ejecta created by the team impact, because that's add actually momentum to the system. So how much material has been actually removed from Dimorphos help us to give that extra push. And that's what we need to understand now. How can we measure it, but also how can we predict it properly? Because if we want to do this in real time, we need to know that the outcome is exactly what we expect. We don't want to perturb it in a wrong manner, right?
I'm listening to everything that both of you are saying, and I'm hearing very strong engineering knowledge, very strong mathematical knowledge. For anybody who might be listening to you who loves space, would love to be part of this, is there any room in these teams for them which doesn't require extremely good mathematical engineering skills?
Outreach.
Outreach, but you're doing that too, it seems.
No, but we will always need outreach, because as scientists, we try. However, it's different, because sometimes you are so into a subject that it's difficult to tell it to the public in a way that everyone understands, and we do need help with that. We definitely need help with that.
Oh, well, there we go. For people like me and you, we can do outreach. Kathrin Altwegg, you are a Professor Emeritus in Space Research and Planetology at the University of Bern, and your PhD was in solid state physics in the University of Basel a little while ago, postdoctoral scholar at New York University, more physics, and 2011 to 2016 you led the Centre for Space and now, what's this word?
Habitability.
So
Yes.
can we live on habitability in space?
It's
How can
not
we live?
Really, can we live on? It's not about humans. It's about, is a planet ready to accept life in any form?
Aha.
Microbes or whatever. It's not building houses.
No, but people are thinking about doing that on the moon. So you have been, you said, retired for 10 years. And you said the wonderful thing about retirement is that you can go into work on rainy days and go outside on sunny days. But you have not retired, not in the least. That is why you're here. You deeply, deeply love your subject. And so let's go into that subject then. I'm imagining that back in 1980, in the physics department of Bern and Basel, there were not so many females there.
No, I was the only one.
The only one. Well, it's really sad to think that 1980 doesn't seem that long ago, and yet in that space of time, look around us right now. We have such wonderful female scientists and nobody blinks an eye. It is really very common and highly acceptable. And so you really did forge a path. And then in 2011... it must have been quite something. You must have been, again, one of the few female leaders in space at that time.
For the Rosetta mission, there were 2 female PIs, one from Italy and me.
Principal investigators. And so talk to us about this wonderful work on Rosetta and what Rosetta was then.
Rosetta is a cometary mission, so we went to a comet, not to asteroid. A comet is just a more cool asteroid.
More cool in
Yes.
what way?
It's actually much more
temperature-wise.
temperature-wise.
But you also love
no,
them.
also from science, it's much more cool. I would claim they are roughly minus 240 degrees.
Which is almost Kelvin.
Yeah, it's 30
Kelvin
kelvins.
Yeah.
And they contain not only the rocks which are left for asteroids, they also have still the ice, the primordial, the pristine ice from the very early solar system.
That is also, I mean, talking about the zeros and the ends of numbers, but to think about that comets have something that hasn't yet been touched by mankind, pristine, to use that word, that is quite rare today.
Yes, that's true. And comets, they are far out of Pluto, so they were cold all the time. I always say they are in the deep freezer with a lot of stars. The deep freezer has a lot of stars, not only 4. And asteroids, they have been cooked in the pressure cooker, and that's the difference between the two.
Well, I'm still on the fact that you've got pristine ice in these comets out in the deep freezer beyond Pluto. The reason it's in my mind is because next week, actually, I will be recording a show on water. And it turns out that one of the principal investigators of water around Europe and she's originally from Australia, said that when she started her research, you could find virgin water in Europe that was not touched by humans. You can't find that anymore in Europe. There's nowhere in Europe where there's water that hasn't been touched by human plastics or flame retardants or something. But in space, we still have it.
Yes, and we now know that cometary water, that's not the same as terrestrial water.
So what is
Cometary
comet?
water has more heavy water. We drink it also. It's in this glass of water.
Deuterium.
But yeah, the deuterium. But we have much more on the comet.
And why is this?
Because the water on the comet has been formed long before the solar system formed. So it's much older than the solar system. So we have a way to look back. It's archaeology, but with a lot of zeros in the years.
It's really amazing, isn't it, to think that you are an archaeologist in space?
Yes, I always wanted to study archaeology.
And how did you end up in physics?
Well, I wanted to have something exact, precise. And that's why I ended up in physics. But I still do archaeology now with comets. And the nice thing is we not only find water ice, but a lot of other ices, like CO, CO2, N2 ice. But we also
we should say, sorry to interrupt you, that carbon dioxide, CO2, obviously at the temperatures you're talking about, is a solid.
That's a solid, yes.
Yeah, it's a solid at those temperatures.
Yeah.
We don't know it as a solid here. Yeah.
Even nitrogen N2 is a solid at that temperature.
Yeah.
And we also found a lot of organics.
Oh.
Among others, amino acid. And there is no life on the comet. Because on the comet you don't have liquid water. And life, as we know at least, needs liquid water. But we still have amino acid, which is a building block of life.
And so what do you summarize from that then?
So the material is mostly older than our solar system. It comes from earlier stages of formation of matter. And so it's universal. And if it's universal, what could have happened here could have happened everywhere in the universe.
So then the obvious question that you've been asked a million times. I'm not even going to bother asking it. What's your answer?
Aliens. No.
Other life forms.
Life forms, it's almost certain that we have other life forms, but not life as we are. It's microbes, probably.
Microbes,
yeah.
Similar microbes?
That's very likely because microbes on Earth, they came very shortly after the Earth really formed and got a little bit... When she formed, she was very hot, 250 degrees Celsius. So no water, no life. But then she got cooler. And then there was the late heavy bombardment with small bodies, asteroids, comets, which probably brought these building blocks of life. And 100 million years later, which is very fast in astronomy, we already had microbes. But then it took 3.6 billion years before humans emerged.
Again, the timelines, the distances, they are very hard for my little brain to comprehend. And actually the timeline of your research also for one human life, it is a whole life's work.
Yes, a mission like Rosetta is 40 years. 10 years of planning, 10 years of construction of the instrument, 10 years of flight. So it's not like an asteroid. To a comet you fly much longer, 10 years. Then 2 years mission, and since then we do a data analysis. And this is still ongoing. So at least 40 years, 4th generation of researchers.
It's like a whole family with little babies of Rosetta scientists popping out. It's truly, well, congratulations to you on everything that you've done for females in science and for your archaeology of space. Aura, you have fallen from the Royal College of Art into the space world. How did you make this transition?
Well, I have to say I'm totally in awe of all the people I'm sitting with here, and I don't know much about space or about asteroids or about comets, so I've learned a lot through listening to you. I'd say that a lot of my work has centered actually on women or women identifying composers, people working in music, but also in science, inventors. So I've always been interested in that without necessarily understanding exactly what achievements these, the hard science is kind of a bit beyond me. But I like this idea that someone sees something in a different way and we can see it or hear it through their eyes or ears. So I really like that idea, like with the idea of listening, you say getting under the skin, but getting under the ear or into the perceptive way of observing that a scientist or a composer or an inventor might have. So I have fallen into, Asteroid Day specifically, but it's not something I'm in any way an expert or, I know very little. I'm very pleased to be here and learn so much.
But you are bringing that outreach, and in fact you used a very important word, the perception, and how all of this maths is perceived, because in fact last year, I think it was last year, possibly the year before, I've lost track of years, it's not 40 years ago, but we had this wonderful scientist, a blind scientist who looks at space through sound, sonification, and I know that's an ongoing project to be able to perceive, because it isn't as if we can all look up into space and see these things. No one around this table can do that. That also requires the engineering of instruments so that we can see out into the cooler box, the freezer beyond Pluto, etc. So the work that you're doing, it's still about the perception of what is out there and how it is perceived. Actually, it's a feedback loop, so it is incredibly important. And so with the knowledge that you have gained from the people you've spoken to, how do you make that able to be interpreted by somebody who is not a scientist?
That's a good question. I have worked on multiple projects with an electronic music composer called Laurie Spiegel, and she's probably well known in your circles, I imagine, for having composed Kepler's Harmony of the Universe, which is sonification of planetary data that was sent on the Golden Record and is still out there. And so through the work I've done with her, it's been really fascinating. And then thinking about data sonifications into the present, I think you were referring to Wanda Merced Diaz.
Yes.
And to me, that idea of listening to the stars is just full of poetry. And in some ways, you don't need to necessarily understand it, but you might get some intuition. And I think a lot of my work is really about trying to tap into that sense of you're nearly understanding, or, like when you listen to music and you're really kind of absorbed by it, but you don't know how it comes about. There's a kind of pleasure in just following that thread, sonic or otherwise. And so I think of a lot of the works I've made, and as I said, they've centered on different people. It's, sometimes I made a project about Hedy Lamarr, who was an actress but also an inventor, who somehow through multiple different iterations ended up contributing to the invention of wireless telephony. I made a project about Henrietta Swan-Leavitt, of the variable stars fame, one of the first women working at Harvard. And so, I've been kind of interested, I guess, in the labor, as well as, I guess you could say, it's not necessarily invisible, but like making work, I don't think of it as outreach, but sometimes my work is about making some information circulate differently, so it makes it visible or audible in a kind of context where maybe it wouldn't usually be seen or heard.
Yeah, and when you're talking about these wonderful women, Hedy Lamarr and various other people that you have worked on their life story, literally it's a life's work. As I look at you, it's a life's work you're dedicating here. You're also making it tangible to another person who doesn't have your mathematical skills, for example, which is of itself another language, but you are making it approachable too. You're making it more approachable, perhaps. So let's move on to siren sounds.
Yeah, so I worked on, not 40 years, but just over 7 years, I developed this project which centered on siren sounds and emergency listening. And it kind of came from thinking about, I guess this is maybe not dissimilar to the way that astronomers or astrophysicists sometimes think, that there are these sounds out there and they might be communicating something to us. And how do we listen? And so with the siren, it's a very, I guess, cohesive or established sound signal. We know, or we've been taught to recognize it a certain way, but it wasn't always like that. And, way back, people might have used conch shells. And now we're receiving telephone notifications, so our phones might buzz, and that's kind of where sirens are going, in this kind of maybe not necessarily auditory direction, more vibratory and textual. And so what I was interested in is this idea of, in a state of emergency or when action needs to be taken quite swiftly, there is this sonic signal, and what happens if we think about it musically and try to potentially recompose this sound? What happens? Are we still in a state of alarm? So one of the threads that runs throughout this project is, does an alarm have to be alarming? And it doesn't always. Does it have to be loud? If you think of, if you're caring for your baby or your elderly parent, you might be listening to the sound of their breath, and that's your siren, so to speak. So there's lots of ways in which we can recalibrate our attention and also the way that we respond to whatever is requiring action. And I guess as part of that, a really important kind of, recalibrating how we listen to the sirens, how sirens sound. But I came up with this kind of working definition of what a siren it can do or does rather than what it sounds like. So it's a call to attention, and then it has an instruction. It's telling you to do something. And lastly, it points to the possibility of future. So really, when you think about it that way, rather than it being kind of catastrophic or apocalyptic, like the sound of end times, we're in a state of crisis. Everyone, I think, understands, especially on days of heat waves like today, we understand that there is a crisis. But really, when you think of the siren as kind of life-affirming, pointing to the possibility of survival, then you have a different reading of it that I hope is more optimistic than this kind of doomsday reading of, sirens are sound, alarm bells are ringing everywhere.
Literally alarm bells, yeah. So on that note then, when we come back to asteroids and asteroid day, and the likelihood, which you said is not so likely that one might hit us, what is the statistical likelihood of an asteroid hitting us?
Depends on the size.
Yeah.
Really depends on the size. So Sabina can also add more, but we tend to think about asteroid impact as this catastrophic event, like the dinosaurs are not here today because of that reason. But these are really very rare events. So we are not, at the moment, what we are here for is not to scare the population about this.
And just on that point, sorry, very rare event, yes, asteroid collisions wiping out things like a whole
humanity.
Yeah, such as the dinosaurs, but not everything at that time. Are there any other impacts of that size that we can see on Earth?
We have witnessed, right, Sabina?
Yeah, so luckily the Earth has this thing that is called the atmosphere that really protects us. So asteroids smaller than maybe 30 meters or so, luckily they burn in the atmosphere. So we've witnessed shooting stars, or what are they called, like fireballs. You might have heard of events such as the Chelyabinsk, where an asteroid exploded above Russia, or Tunguska, which was maybe about 100 years ago, that flattened kilometers and kilometers of forest. So they do happen. However, they are indeed not this dinosaur killing asteroids.
We have no record as we can see Earth.
But what we do have on Earth quite a lot, there we find meteorites, right? So these are remainings from maybe smaller objects, and we also find impact craters.
That's what I mean. So the impact craters, are there any large ones there?
The 2 points we need to consider is we are also blind on the direction of asteroids that come from the direction of the sun at the moment. So this was a case of Chelyabinsk. So we didn't have enough time to warn the local population. And so the key of Asteroid Day or activity like international cooperation is like I1 and same page is really to flag these are international UN recognized body.
Sorry to interrupt you for my ignorance again. So with that particular example, and I can remember the video footage shot on a telephone or something at the time, mobile, you said we were blind because it was coming in the direction of the sun, but the Earth rotates.
It's more like from their orbit, so which direction, we cannot point telescope in certain direction. So there is going to be actually a new telescope to be sent in space that can really actually warn us on those directions. So there are specific direction of the sky where we cannot see what is coming. And so this undetected object is what we care about, because even if they are small and might cause local injuries, you want to care about, right? These are the beauty of asteroids, I think, is one of the few events that, if tracked well, as the international cooperation between NASA and ESA is doing, we can predict them well. So, but we have to catalog them.
And I think you'd like to come in on this.
Yeah, I think we might see it in advance, but we may not be able to do something if it's too big. 30 meters, that's not a problem. 100 meters, probably we can deflect if it's a kilometer. The dinosaur asteroid was 12 kilometers in diameter, 72,000 kilometers per second. That's not 6 kilometers per second. It was 72,000 kilometers. No, per hour, not per second, per hour. But still, you can't do anything. You can just warn the people, but it won't matter. Actually, it won't matter.
I suppose that's why. Well,
I don't know how to follow that.
Let's give
what do you want to know?
Let's give a hope in the sense that that's what space agency are here for. So we tested that because if you know well in advance, you can act in advance. But also there are other techniques we can.
Yeah, but
right?
I guess such a big asteroid you can't do anything. But I always claim if this asteroid would not have hit the Earth, we would not be here.
That's
because
positive.
we would have the dinosaurs here.
So maybe it's meant to be.
Yeah, it's meant to be.
Luckily, these very, very big asteroid impacts, they are very, very rare.
Yes.
I think what we have to worry about are more in the 100-meter size, because these ones would not kill the entire population. However, they would still produce localized damage. So if it falls on a large city like London, New York, then that could really be catastrophic. And these are the ones that we can do something about.
Yeah, that makes sense.
Yeah.
But let's be clear, for the big ones, that's it.
When you say they're extremely rare, that's why I was asking about. Thank you. I love a bit of honesty. Nothing like a bit of honesty. When you're saying they're rare, I mean, I think it sounds like we have an N of 1 at the moment because we can only look at the dinosaur craters. So for Earth, we don't have. I was wondering, do we have any other similar examples? But it sounds like not that we can see.
No, we do have big craters. There's one in Germany.
Oh,
A relatively big one.
No, not as large as the JAXA.
Yeah, maybe, but still, that wouldn't have been good.
no.
And there are models showing that if an asteroid of a kilometer size drops near Tenerife, this would give a big tsunami in Spain, and then the forest would burn and so on. So it would.
Does anything keep you awake at night?
No.
No. You don't worry about things. You just have a very kind of, this is how it is.
That's how it happens. You know, in the last 500 million years, we had 5 apocalypses, 5 times where life almost died out on Earth.
So every million years.
Every 100 million. Every 100 million years. The last one was 66 million years ago.
Oh, we have a few years left.
Yes.
Okay, perfect. So we have a few more. It's a bit like the earthquakes in California or something. So we have about 36 million years left to go before we need to worry.
Yeah.
Something like that. We're okay. A few hands just down like. Let's move back to your projects right now. So let's think about. We spoke about DART. We spoke about Hera. We haven't spoken about Ramses yet.
which is in the next cool
Yes.
chapter.
Yes.
Or let's say if you want to look at it more as episodes, NEO's episodes. So so both me and Sabina work on Ramses, and what is exciting, we are going to have an asteroid coming very close to the Earth in 2029. And
Now,
this is
I think,
Apophis.
given what we've just talked about, how big is this asteroid?
I don't
It's
remember.
about 300
Yeah,
Yes.
meters
300.
across.
Meters.
For quite a while, it was believed that asteroid Apophis might hit Earth. So that's when the international collaboration of alerting if dangerous asteroids are coming towards Earth was alerted. Luckily, after observations and after a lot of scientists did observations on this, it was excluded. So it's not going to hit Earth, absolutely not. However, it comes close enough that we can watch it and we can actually go to it. So it comes as close as the geostationary satellites. So really, really close.
That's just like shaving the skin off us or something.
It's extremely close, and it is coming in 2029, and people across the world will be able to watch it just moving across the sky.
Right. Well, we have an awful lot of information held in those satellites up there. Is it going to knock out all sorts of things that we currently rely on?
No, so it's not actually smashing through the asteroids, but it's coming as close, but it's not going to destroy the near-Earth
The
artificial
satellites.
You know,
satellites.
the satellites are all in one orbit.
Yeah.
Yeah.
Just a ring.
Mm.
And Apophis will not hit this ring.
Are you sure about that?
Yes.
Yes,
So the surety comes from maths.
definitely. Math, physics,
Observations?
observation, predictions.
And so of all of these things then, when we think about the frontiers of robotics and AI and the maths and the science, the language of maths, it's been a while since I did any hard maths, but it has that moved on? Has that changed in any way in order to describe space?
It's probably the computers which have changed the way, because we can deal with much more data.
So it's the handling of the data that's
Yes.
changed more.
Data, the speed of which we can
The
do maybe
And
stuff.
equation
and-
and the forces are still the same. So
And just the speed at which you do calculations, because so what I do are numerical simulations, and what we do today was not possible 10, 20 years ago, just because of the numerical techniques and also of the computing power. So this massive advancement in computing power really helps us reach another level of what we can actually study.
And so with that computing power, have your aims changed as well?
Well, the aims are still to understand asteroids and how they formed and, well, the universe.
Just those little
Still
aims.
a big questions still there.
And then you also mentioned something very, very important, which I think we can both recognise as important. How you see these, the observation techniques and the measurement techniques, they've also, I imagine, changed as well, because they're becoming more and more precise.
yes, and we have telescopes which have much higher resolution, much larger field of view, so we see more of the sky.
And when you're looking
And you observe robotically. You don't have to sit at the telescope and look through it the whole night.
And when it comes to looking at what's out there and analysing the data that's coming back as well, now we can use AI and machine learning and everything to scan what's coming in. How good is that compared to the human eye?
That's very good, I have to admit. Astronomers already fear a little bit that they will be replaced by AI.
And what is the next job then? For if astronomers are worried, oh my goodness. I want to stay with you actually, Kathrin, because you've spent your whole life working on comets, and we spoke about the 40-year horizon of the work that you've done so far, and you're continuing it. How does one remain committed over this length of time?
Well, it's a little bit, you get, it's like a drug. You get
You get high on comets.
High on comets, yes.
And for you,
You know, I built this instrument together with my group, and that was my third child. I have 2 daughters and Rosina.
I won't ask you which one's more important.
It depended on the face, yes. And I was really sad when Rosina left home. And I was even more sad when it crashed.
Yeah. That must be, I mean, that's something that I think must be deeply hard to bear when you're spending years of work building something and then you're putting it out there, literally letting it fly, launching it, and you have to let go of all that technology, which you're hoping will last numbers of years into the future when technology is already changing so fast. How does that feel?
Well, the launch was, on one hand, it was beautiful. The Ariane went like a big rocket, and Rosina with it. But it was also sad. It really felt like a loss. And I was just hoping that Rosina would behave in space. You can't do anything once it's launched.
You have to let them fly.
Yeah. You have to let them fly.
But
you can still change software. That's all you can do.
And then also, again, just to emphasize, this is teamwork. You're building teams of people around you. And, you know, as a PI, a principal investigator, how did you find the team members?
They were great. I always had great members, all idealistic. They worked really long times, especially during the mission when the instrument was measuring 24 hours, 7 days a week. We had to look after the instrument and people just didn't want to stop work.
So it really is a drug.
Yeah, it's a drug. It's a drug. But after the 2 years of mission, I was really done.
Which is why that you, even in your retirement, it's not quite retirement, and you are emeritus professor. That's not quite emeritus. You're still there.
So the good thing was Rosetta was crashing, and I was crashing at the same time. I got retired.
That is terribly sad. Kathrin, I need a little bit of uplift here from you.
No, that was great. After that, I didn't have any administration work, no students, no lectures, just research.
Okay, I can
Great.
understand that.
That's really great.
I do understand. I know enough academics to say that life gets a little easier when you lose the students and you can focus on the research again.
Exactly.
So in your retirement then, what would you like to do in the next 40 years?
Well, I will continue with data from ROSINA. Look at them, find more organic molecules, prebiotic molecules, as we have done. And on the other hand, I will go outdoors when the weather is nice.
And what is your prediction for the things that might be found through great research in the next 10 years, let's say, which is a short horizon, I realise, in your world?
Well, there will be an X-Comet mission launching in 28 or 29, Comet Interceptor. And that will be a fun mission. It's a small one. It will go in a parking lot outside of the Earth and then wait for a very new comet. A comet which comes for the first time into the inner solar system. And we don't know. It has to come first.
But when will this comet come?
We don't know.
Or you're just parking it there?
Yes. And wait. Be patient.
Where did the money for this idea come from? Because it's quite hard to find money for research. So how on earth did you find money to park something up there just to wait for an unknown quantity?
You know, the parking space is not expensive.
Well, it's getting a bit crowded up there.
Yeah, still, that's okay.
You have to build it and put it up there. That's expensive.
That's expensive. And then it can wait for a few years.
How many years?
It depends on the patience you have.
Well, I mean,
probably.
If you don't know what comet's going to come, how many comets do we have travelling around us? And not that many in my lifetime. I mean, I've known...
we have comets from the outer solar system almost every year. But most of them don't have the right orbit. So we cannot meet it.
Right.
So, but we have to wait for one.
That's a bit of news I didn't know about. The parking lot for a comet. Just sit there and wait till it comes by. But that's lovely.
I told you, it's a fun mission.
But it's very fun mission. I do like that. Let's move back to the art world a little bit. So you're hearing all of this. How did you get into the asteroid world?
Actually, well, it's a bit of a long story, but as I said, I made this work about women in electronic music. That led me to look at women in computing. Then I discovered these women, early astronauts, actually human computers. So before there were computers, they were humans who were computing data. And because it was tedious, time-consuming labor, it was also badly paid, and it was mostly women doing it. So that kind of led to one thread. And then similarly, you were talking earlier about guns or projectiles. I was looking at women working in World War II with early computers that were also studying the trajectory of ballistics. So I kind of follow where the research takes me. It's very, I'd say it's like there's an improvised quality to it. I don't necessarily know where I'm going to land. And then through this project on sirens, in the middle I was invited to Harvard to show this piece about women astronomers in the original observatory, which was an incredible, like I think it was 10 years after I'd made it, I was just invited to show it there, and it was very moving also to look at the original glass plates of, people like Henrietta Swanlevit. But through that, I met someone who worked closely with Wanda, Kimberly Arkand, who's connected to the Chandra telescope and has been working for it, I think, for 27 years. So through talking to her, I still am really fascinated by data sonification, and that led me to Wanda. And then Wanda kind of introduced me to someone from the Asteroid Foundation here in Luxembourg, and then I got invited here. So it's
Well, welcome.
a strange journey.
And you are here, and you're not just here to show up as a person, but you also have something that is on display for people to go and look at. So tell us about this.
So when I was talking earlier about the Siren project, it started off as a kind of sound project and then a short film. And in the end, I made my first feature film. So it's a documentary film about sirens and emergency listening, many different chapters. And so, for example, there's one in Fukushima, which thinks around deep time and nuclear toxic waste, which is also, I think, relevant here. We were talking earlier about warnings, like how will we warn the distant future? This is a really interesting question that obviously goes beyond sirens and sound, but it's interesting as a kind of thought experiment. And then along the way, I was invited to do a kind of installation. So before I finished the feature film, to do a kind of 3-screen installation that thought about, in that case, I divided into the life cycle of the sirens at the factory, the sirens in situ, and then a siren graveyard or cemetery. And so that's currently on display at an exhibition called État Brut. I don't know if my pronunciation is worthy, at Kunsthalle Esch. And it's a wonderful show. I'm very honored to be included. And it's a nice coincidence because I was in the space yesterday, and obviously I'm with these wonderful astrophysicists and scientists today. So it's a strange series of constellations.
A lovely constellation of different people that you've met and pulled together, and you tell the story, you weave it all together through art and sound and speaking about it as well. So that's a wonderful thing. Just to wrap up then, thank you all so much. I know you're quite tired because you've come from various places and you've got a full-on day tomorrow. But you've spoken a number of times about the biological material that has already been found on asteroids and comets. So what do you think about that? What is the space for a biophysicist, a bioastronomer in your world?
You have to be a little bit careful. It's prebiotic material. It's not biological material.
Prebiotic.
We have not found any biological material so far.
But
it's building blocks of life.
Right.
It's not life.
But you found
biological material would be life.
Amino acids and things
Yes,
like this.
we found amino acid. You also find them on asteroids, quite a lot of them. But asteroids have been altered. They have had liquid water. Most of them, they are changed from the pristine material.
And so if you were a young person today and you had to think about what subject to study, what would you advise young people who want to work in space, because it's a hugely different scene in space?
I think it doesn't really matter that much, because in my team I had geologists, I had chemists,
Theologists.
geologists, yeah,
Geologists.
We also worked with theologists. We did work together with them.
Oh.
But yes,
The meaning of life and all that.
yeah, the meaning of what is life.
What is life?
The question of what is life.
That's another show entirely.
We had software engineers, we had electrical engineers, mechanical engineers, laboratory technicians, secretary who had to do the paperwork. So there are a lot of ways you can end up in space research. It's not only, you don't have to be very good at mathematics. There are ways around it.
The ways around it. I think most of those, apart from the theology and the secretary, I think the others did involve maths. But that's okay. I love maths. And to you ladies, what would you suggest? I mean, I know you're both younger. You're not retired yet, but
I don't think I will ever.
I think it seems like it's a lifelong. It's a vocation.
Passion?
It's a vocation. Yeah. So for your students, you are also both at universities.
I think, as just said, there is different ways where careers can lead you nowadays. And now, even with AI, if you are in computing, probably you could really work in different sector. And for the space sector, except if you want to work on asteroids, but there is also human spaceflight. So anything that is related to medicine, manufacturing in space, are all things that will take you on this career. So I think it's more about taking the opportunity when they come along. And this is how I see my career. I didn't ended up working on asteroids knowing it at 10 years old. It came up through my study and through opportunities. So I think my message is just don't be scared, follow your passion and catch the opportunities when they come.
Yeah, I agree with what Stefania said. Pick a subject that you really like, and then everything else will come along, because I think what matters most is perseverance, because life throws stuff at you, and you have to continue. So if you really, really like it, you'll end up eventually there.
And from your perspective?
About being
to
Asteroid.
young person, you also teach at the Royal College of Art. So to young people there, do they feel strong in their vocation? Art as a choice, as a career, it's a vocational choice from the start.
Yeah. Oh my God, it's a can of worms. The question is very difficult because as a career, it's probably not as stable as any of these more kind of scientific careers. But I don't know. I mean, I think, probably I agree with everything you've said. I think it's important to be passionate. It's really important to persevere. It's important to be a good collaborator. I think in every single sector there is to have good people skills and to like being with other people. I mean, I know there are some careers you don't have to, but for the most part, and I remember my father said to me when I was very young, he said exactly that. Choose a career you like, or, an activity that you feel passionate about, because that will carry you through all your life. Because food, after an hour, passes. Even relationships don't necessarily last that long, but a career or a passion is for life.
Well, I think on that note, we will end the show. Thank you all so much. Thank you for coming to Luxembourg. Thank you for everything that you continue to do in your life's work, your vocation work, in your retirement as well. We're delighted to have you here. It is a real honour to have you here after everything you've done for women in science as well. And now we have, you've set the path with a beacon ahead of us so that other women can follow in your path. And we will watch that car parked spacecraft up there and see if what comet will come by, and when it does come by I will think of you and I'll say that was there for a reason, and I'm hoping that you'll be here to see it, because we don't know how many tens of years in the future that will be the case. Thank you so much. Please do enjoy Asteroid Day here in Luxembourg. We have an ongoing and increasing number of activities around the space industry here in Luxembourg, and of course send us photos of anything that you see. Shooting stars, make those wishes as they come and they get burned up, the littler ones, through the atmosphere, and we'll be back with another show in just a week's time. Thank you.